Earlier, I mentioned that the time is right for modern application development. For a fast growth company or even a traditional financial services institution trying to innovate and compete, the overhead and inflexibility of a monolithic application is unacceptable. With the shift to microservices, one of the main benefits is each service can have its own fully decentralized data store, and each component can also be changed and updated quickly without impacting the entire service, and while reducing the blast radius if a microservices goes down. You can now innovate and respond to market trends faster with lower risk. As microservices-based applications grow in their size and complexity, they also run into issues like orchestration, state management, error handling, and observability. I would like to welcome Alan Terletto, Field CTO at Redis, and Viren Baria, co-creator of Netflix Conductor and CTO at Orcus, to talk about how to implement best practices design patterns to build and scale microservice apps reliably.
Hello, and thank you for joining us. My name is Alan Terletto. I'm the Field CTO at Redis. Today I'll be talking about microservice architecture. I'll introduce critical microservice patterns and show you how you can easily implement them with Redis. But that's not all. Joining me today is Viren Baria, CTO and co-founder of Orcus. Viren has a decade's worth of experience in the field of microservices, having worked with companies such as Google, Netflix, and Goldman Sachs. As many of you may know, Netflix was one of the earliest adopters of microservice architecture, and as an organization, continues to be one of its chief evangelists and practitioners as the architecture continues to evolve and mature today. So Viren brings his lived experience of not only being engrossed in this evolution, but also being one of its key contributors with his co-creation of the Netflix Conductor open source project, a cloud-native engine to run workflow orchestrations. We'll hear more about Conductor, the broader topic of orchestration, and where this all fits in within the context of the microservice architecture later in this presentation. Now, I'm sure everyone watching this live or on demand already knows about Redis. However, if you missed our recent announcement at Redis Days San Francisco, you may not have heard about Redis Stack yet. So let me quickly introduce it, since I'll allude to it later on in this presentation. Redis Stack consolidates the capabilities of the leading Redis models into a single product, including Redis JSON, Redis Time Series, Graph, Bloom filters, and even Redis Search for secondary indexing and SQLite querying and search. It also packages our development visualization tool called Redis Insight and our supported set of Redis clients called Redis OM or Redis Object Mappers across major programming languages. This allows developers to have everything they would need to develop with Redis end-to-end with minimal installation and user experience friction. Speaking of friction, let's segue with this concept in mind into our topic of the day, microservices. Now, if you're new to microservices and have begun to research the topic, or maybe on the other side of the spectrum are considering to scale its deployment beyond 50 or 100 microservices, you've likely found that it's a very busy space. There's a bunch of new architectural patterns, new architectural concerns, new technologies, a laundry list of pitfalls to worry about, especially as you scale to hundreds of microservices, and most of them are centered around the data tier. Now, if you stop and think about it, that's not something we worried about as much in our monolithic SOA architectures. In an SOA architecture, we had one or a couple massive databases and a bunch of services broken up by subdomain. Life seemed to be easier back then, right? But was it? What happened when that massive database had an outage? And what happened when you needed to provide a quick fix to your service, but were told that you needed to align to an enterprise release cycle, or go through an entire integration QA cycle with a bunch of services that don't impact yours? I've been there, and it wasn't always fun. So now we're migrating to a microservice architecture, which at its core has the characteristic of componentization. There's another way of saying isolation, which is defined as independently deployable, fine-grained services centered around business context. This means that in the purest form of this architectural style, that a microservice should not share a database with another microservice outside of its business context. Now that's a big deal, which will have ramifications and create complexities, specifically in the data tier, which we're going to cover in just a bit. So where do we begin? Look at that. It seems in all this noise, Redis is right there in the middle. Well, it's kind of off to the side on the right, but you know what I'm saying. Redis is fast becoming a de facto standard across microservices architecture, not only for its bread and butter use cases like caching, session, and access token management, but to implement some of the most critical architectural patterns specific to the data tier, which, as we mentioned, is where practitioners typically experience pitfalls. You've noticed I've also circled a few architectural patterns that are core to microservice architectures. As we progress, we'll cover these patterns, show you how to identify them, and how Redis can be used to simplify their implementation. Let's start with a conceptual architectural diagram of a microservice architecture. If you have seen a microservice presentation before, you might be asking yourself, why is this one so busy? Normally I only see 2 or 3 stateless microservices and maybe a message broker between them. Well, that's all well and good when you first start, but when you get to 20 microservices, 50 microservices, 100, 1,000 microservices, it's not so simple anymore. Isolation, eventual consistency, empowering small teams to make independent technology choices for their business context, all have architectural trade-offs, so need to be accounted for if you want to avoid those pitfalls. But don't worry, even if this diagram seems like you're staring into the matrix, we're going to decompose it into its critical architectural patterns, which we just highlighted. And by the end of this presentation, you'll be able to identify them on your own. So take the red pill, let's dive deeper, follow me. First up is domain-driven design, or bounded context. Remember, isolation is a key characteristic of a microservice. We want to make sure each microservice is manageable by a small team, sometimes referred to as a two-pizza team, which is not dependent on anyone else in the organization to communicate or make decisions or even to deploy in production. Truly an agile team. In our diagram, we started with a domain of payment processing. If you think about it, that's way too large of a domain to be managed by a small team because it includes fraud detection, settlement, credit, and more. So what if we chose a subdomain like fraud detection? I focused in on the first 3 microservices so you can see they're all fraud related. But it's still too large, right? This small team would need to manage digital identities, statistical analysis, and transaction risk scoring. That's a lot. So as you see, based on domain-driven design, we can reduce further to a subdomain of just digital identities, which sets our bounded context, and separately another subdomain for statistical analysis and transaction risk scoring. Now before we move on, notice something else. Each microservice has its own data model, or if you're not using Redis, its own database. As you recall, this is the purpose of isolation, which drives agility and time to market. In our example, the small autonomous team has chosen to use Redis JSON for its digital identities to perform JSON path querying and search. However, a different team that owns the other bounded context, they decided to use Redis Bloom because it's going to be a better fit for probabilistic analysis. They also chose Redis Stack because it gave them access to multiple models for computation of transaction risk scoring. The point here is that each team chose an optimal data model, specific to the goals and SLAs of their unique microservice. And by using Redis, they didn't need to learn 3 distinct database technologies to do it. They just chose a different data model. Think about that for a second. What are the ramifications of bringing a new database into your enterprise for each microservice? How do you scale procurement, security assessment, training, DevOps, meeting enterprise-wide SLAs? This is what I meant by starting to feel the pain as you scale beyond a handful of microservices in production, specifically at the data tier. With Redis, it's just one database. Choose your model, and let's dive deeper. Now that we've isolated our microservices, we need to account for the trade-offs, namely, how can they communicate with each other without breaking isolation? In other words, stay decoupled. For this, it's common to bring in a publish-subscribe message broker into the architecture. In other words, make inter-service communication event-driven and eventually consistent by treating each message between microservices as an event. Since we're already using Redis for data storage, let's leverage another of its data structures called Redis Streams for its publish-subscribe capability, including consumer groups. As all Redis data structures, it's lightweight and easy to use. You can be up and running within minutes to scale out your event streaming between microservices. So now when a microservice finishes its work, it can publish a message onto a Redis stream, and all subscribers onto that stream can optionally react to it, or ignore it, or miss it because they're unavailable and catch up later once they recover. This is one of the benefits of isolation and eventual consistency. So how do we implement publishing onto that stream? Well, the first thing people do is implement the dual write pattern at the application layer, which means they commit a local transaction for purposes of data storage and then separately publish an event to a message broker. Now, this works, however, exposes them to a variety of architectural concerns specific to failure scenarios. What if you committed and didn't publish, for example? A solution to this is called the message relay and event sourcing patterns to remove the need for two distinct writes at the application layer. With Redis, we can leverage Redis Gears as our message relay. Gears can listen for specific state changes and then write behind to a Redis stream for event storage or downstream processing without adding any code to the microservice. This is known as event sourcing. In fact, the stateless application of the microservice stack would not even be aware that this happened. This process would be completely isolated within Redis. So you can implement it seamlessly and uniformly across hundreds of Redis databases. So your SRE team is not required to patch each microservice differently to provide enterprise-wide SLAs. Speaking of SREs, those same events can be pushed into a Redis time series database for KPI tracking, alerting, and other observability needs. By the way, here's a visualization of that stream using Redis Insight. Of course, we also have integration with the most popular observability platforms of the day, Grafana, Datadog, Dynatrace, and others. Let's now move on to another popular pattern that focuses on data model optimization and isolation of components, namely databases. In the diagram, you see that one microservice is the system of record for persisted transactions, while the other microservice only serves that data to upstream consumers in real time, for potentially a different business context. If we use the same database for both microservices, we could potentially couple their deployment, breaking isolation, and we could only optimize for reads or writes, but not both. A solution to this is the CQRS pattern, which segregates the responsibility for writes, known as command, and reads, known as query. With this approach, we would maintain isolation between microservices and optimize both read and writes. Perfect, right? But what's the catch? How do we keep data consistent between heterogeneous databases and potentially transform the payload so it's optimized to the data access pattern on the query side? One of the easiest ways to implement this pattern is to use a CDC, Change Data Capture platform. And guess what? Redis has one called Redis Connect. Using Redis Connect, we could seamlessly track change state on the command database and replicate those changes as they occur, with the added benefit of transforming the payload so the query database needs only to ingest and serve. This is a complicated pattern to implement on your own, but made easy with Redis Connect. Just configure and go. Now, we already covered a lot of ground, but we bypassed something that is critical in a real-world architecture. Specifically, what if we needed to perform a distributed transaction? In the monolithic world, we would use a two-phase commit on our one or two systems of record. However, that's an anti-pattern in microservices because it breaks isolation. This is where architectural patterns called sagas are typically employed. One of the ways to implement a saga is to make it event-driven and perform choreography. But that's complicated. It has its own trade-offs. Another way is to implement orchestration-based sagas, which at this point is actually a great transition to our next speaker, who has been working on this for over a decade. As mentioned earlier, Viren was co-creator of Netflix's open source project Conductor, which is a cloud-native engine to run workflow orchestrations, perfect for orchestration-based saga implementations. Let's let Viren describe the trade-offs to choreography and orchestration, and how Conductor can be used to make microservices easier. Viren, the digital floor is yours.
Thanks, Alan. Hi, everyone. My name is Viren, and I'm going to talk about the orchestration pattern for microservices and how it helps simplifies the microservices. Let me give you a brief background on my experience with microservices and some of the patterns we applied to simplify the architecture. So prior to founding Orcus and my time at Google, I spent time at Netflix, where I saw Netflix's journey into its second major pivot as a company into the largest content production studio in the world. We all know Netflix is known for its early adoption of microservices and running them at scale in the cloud. The time when I started at Netflix, the company was undergoing a major shift in becoming the largest content producer from becoming a licensed streaming player. Now, this pivot also meant we were constantly building, changing, and testing new processes. And Netflix had a unique approach to building the studio, very engineering-driven focus here, experimentation and rapidly experimenting and changing the processes. We had a large number of microservices, tens, if not hundreds of them, responsible for various different tasks, and that allowed us to scale and build new things very quickly and push it to cloud. Now, what we saw was the need to orchestrate the services and needing to decouple the business logic from the underlying implementation of the services themselves. What we saw was what we were doing to orchestrate the services was either writing more services that would then orchestrate the other services, or actually embedding the orchestration logic into services itself. Let me give you an example. So take, for example, an encoding service, right? That takes a file, converts into format for various devices, and then it would call the deployment service that takes the file and puts it into the CDN. Now this does not scale operationally. As the complexities grow, this becomes unmanageable. And what we saw was we had started to build a distributed monolith. Like our application logic was all over the place. One change meant talking to 20 different developers to figure out where things were and get them to migrate and change the wiring of the flow. Also, let's not forget the migrations, right? Like as we were building things and trying to onboard to new platforms, how do we kind of safely migrate things into the new frameworks, platforms without kind of breaking the operational aspect of it? Now, of course, there are many ways to solve this problem, as Ellen had kind of pointed out earlier, right? And we'll see shortly, why we chose orchestration as a way to solve this problem. Now, orchestrator pattern is a well-known pattern where essentially you have an orchestrator, ideally a distributed one, so it provides high availability, who is responsible for dispatching the calls to underlying microservices to orchestrate a specific business flow. And it hides all the complexity of orchestration from the microservices, right? And then microservices can essentially stay, and follow single responsibility principle. They do one thing and they do one thing well. Ideally, they are stateless and they can scale. And let's also not forget the change aspect of it, right? Business processes are not static. They change, they evolve, they grow in complexity over the time. And an orchestrator essentially allows you to hide that complexity and allows you to kind of move that complexity of migration, version control, everything into orchestration from the services. And this was the reason why we chose the orchestration pattern to solve the problems that we were facing with the microservices. To demonstrate this further, right, let's take a quick example of a hypothetical loan processing application. Of course, this is a very simple version of it. Reality is a lot more complicated. But to demonstrate, let's think about an application that processes loans, right? And essentially you have like 5 different microservices. One that does identity validation, does some risk scoring using some machine learning model, maybe an API that calls into validating the collateral that is put against the loan application, does some rate calculation, and finally sends out the notification. Looks pretty simple, right? Like you write 5 microservices, wire them up together, and push it to production. Now, we all know the reality is very different from that. And beyond just handling those wiring of the flows, you also have to now think about how do you handle errors? What happens when something goes wrong? How do you put in the compensation flows? In the end, we are talking about distributed systems, right? How do you build observability for your SREs, for your operations team? And what we had seen was, almost 70% of the time was being spent on doing this kind of work. Now, not to say this is not important, right? This is really important. You don't want to push a production application without actually handling this kind of flows. But again, it's a repetitive pattern. And ideally, an orchestration framework can take care of this, right? And that makes a very good use case and a case for a very well-formed orchestration framework. A good orchestrator essentially handles scenarios beyond day 0 once you push things out into production. Think about day 1 to day end scenarios when your application is running in the production and is in the hands of SREs, DevOps, business operations. The orchestrator framework takes care of all the common concerns around availability, reliability, things like error handling, retries, rate limiting, so you don't end up DDoSing your own services or a third-party service that you rely on, right? It handles the compensation for you so that, when things go wrong, it is able to kind of recover from those or at least make the right adjustments. And it's built for observability, more important than anything else, right? Like SREs probably want to know the latencies for services. They want to know when the service should be scaled up or scaled down to save the cost on the cloud. Operations wants to know when something goes wrong or when the customer complaint comes, what actually happened. They want to probably retry and see or restart and provide the right level of services and SLOs. And most important thing, right, as I mentioned, being able to version the processes. What happens when you have a new risk scoring model and you want to safely test it out and see whether that works or not? What if this is a user facing application and you want to run an A/B test to see what's the effectiveness of the new flow that you are proposing or the product manager is proposing? How do you kind of do that? Orchestration framework should be able to kind of do all of these things. And this is what we did with Conductor. So we solved this problem of orchestration with Netflix Conductor. Conductor essentially is a distributed microservices and a workflow orchestration platform. And it handles all the scenarios we talked about, right? In terms of, being able to provide all the availability, reliability, version control, and all the aspects of error handling and things like that. And at the same time, being able to wire up microservices, right? The most important part also is that, it takes the business logic out of microservices and into a centralized place. So, they can be independently managed, visualized, and changed. One other thing is we live in a world where, you have a heterogeneous application development environments, different languages, platforms, framework, SDKs, even cloud vendors. So Conductor was built to be very much of language as well as platform agnostic. We had workflows, and it supports workflows that could have a combination of Java for API calls, maybe Python for ML models, C++ for image processing and stuff like that. And more importantly, it helps orchestrate not just microservices but also serverless. We had workloads running in containers, for example, functions, and also let's not forget about the existing applications that are yet to be migrated to the new framework, right? How do you safely integrate with them through various well-known integration patterns and have time to migrate everything? Conductor was built at Netflix. It was open sourced under Apache 2.0 license, so you can download and use it however you want to. And in fact, since open sourcing, it has gone places. We know today a number of Fortune 500 companies rely on Conductor for their mission critical flows. At Netflix itself, it's being used by 50 plus teams, and it's a de facto orchestration engine. It really operates at scale. And Conductor essentially solves the problem and more importantly, implements that well-formed orchestrator. It gives you all of those things as a UI that allows both developers as well as the operations team to look into the state of the flows and debug the problems. And once it is fixed, continue executing the flows. And the most important part is that it helps engineers focus on what really matters, which is focusing on their application development part of it and not have to worry about how do I scale this, how do I handle durable flows, like what happens when something goes wrong, how do you recover that? You never have to worry about those things with Conductor. And let's not forget about the existing applications, right? As I mentioned, right, like once you build a new framework, you can't necessarily stop all the new feature development and get everyone to migrate. So Conductor was built such a way that we built versioning as a first class citizen as part of Conductor and not as an afterthought, so that we could create alternate flows with new versions, which had the new implementation of the existing services that we were migrating, test it out, and safely roll them out. Conductor can run same workflow with multiple versions in parallel. You can A/B test, you can do canary testing before you can actually roll it out. Now let's dive a little bit deeper into the overall high-level architecture of the conductor. This one shows a very high level in terms of various components in conductor, right? At the heart of conductor is the orchestrator, which essentially is responsible for managing the states and executing orchestration across multiple microservices. It interacts with the task workers, which are your microservices or serverless or even monolithic applications through HTTP and gRPC based endpoints. It integrates with well-known eventing frameworks like SQS, Kafka, Nets, AMQP that allows us to essentially integrate with either other applications which are not on Conductor or third-party apps which were not possible to migrate to Conductor. And underneath that, essentially, it relies on distributed queues that allows us all the works to be scaled out. For queuing, we rely pretty much on Redis, and it supports all flavors of Redis, right, including standalone, Sentinel, cluster, enterprise Redis, and all the state is managed inside a persistence data store, which again, Redis is one of the database that we use. And community over the years has supported things like Postgres, Cassandra, MySQL. And this architecture really allows conductor servers to be very stateless in nature, which means you can scale them up and down based on the workload and not have to worry about pre-provisioning based on the capacity estimates. All right, so how do we essentially get started with Conductor, right, and help simplify the microservices orchestration? As I said, Conductor is open source under Apache 2.0. If you go to github.com/netflix/conductor, that's the repository. You can find various releases there. You can download and build it. And if you really like it, please give us a star. That really helps. We have 2 active communities on Slack and Discord. I have the links here. Feel free to join. We are happy to support there. And again, Orcus was founded by the founding engineers of Conductor, including myself. And we are on a mission to help developers simplify their journey into microservices and distributed applications. We have a playground at play.orcus.io if you want to download and just give it a try and look at the UI and run some workflows. So that's about Conductor. I'll hand it back to Ellen now. Thank you all.
Thanks, Viren, for that deep dive into orchestration-based sagas, for that introduction of Conductor, and the overall value orchestration can play at the microservice level. To round out our conversations about patterns, I just want to touch on globally shared data. We spoke a lot about isolation, but there are use cases for where you really need to share that data across all the different microservices. This usually happens at the API gateway level. Of course, we're talking about session state, tokens, bread and butter use cases for Redis. But of course, you don't want to have Redis as a single point of failure for your entire microservices architecture. And that's where Redis Enterprise comes into the picture. Redis Enterprise provides those enterprise-grade capabilities, including 5 nines availability, so it never gets brought down and you never have that single point of failure. I hope through this discussion, you're able to see this diagram and be able to now identify the different patterns. Domain-driven design, optimally choosing each data model, leveraging an event broker for event sourcing, using tools like Redis Gears for message relay and transaction outbound patterns, having that overall integration, CQRS, where you can replicate data from command to query without breaking isolation, and of course, distributed transactions leveraging choreography or orchestration-based sagas. If you're interested in this topic and you're interested to go a level deeper, check out our blog on the New Stack about where Redis fits into microservice architecture. We actually have a Redis for Dummies book. We recently did an IDC info brief where you can get a really good understanding of how far Redises have come within enterprises. I want to thank you all so much for joining this session. Thank you all for joining Redis Days. I hope you enjoy the rest of the session or can catch them on demand. On behalf of Viren and on behalf of Redis, cheers and thank you.
It was really exciting to see how Redis Stack and Conductor Workflow Orchestration provide a simplified operational platform that addresses the challenges with building and deploying microservices-based applications at scale.